you have questions on exactly what is meant by all this and how you can figure out where bulk flow takes place, where diffusion takes place, and what the levels are where diffusion takes place, like at the beginnings of the capillaries versus the end of the capillaries at various, so we can pretty much figure out what's going on here, and we can figure out what's going on here by, whatever this is, which is given by this value, it's got to be the values towards the end of the capillaries. The values coming in here, at least the O2 and CO2s coming in here have got to be what's going on here. Then you have to pick the alveoli spaces to see what's on the other side. And you should be able to see how it fits with a curve like this, because as this diagram is showing between here and here, this is like, happens to be 75%. So that's it. Remember, hemoglobin requires 4 oxygens. Once you get rid of the first oxygen, the other 3 fall off pretty easily. So the first, these are going to fall off over here. So where are these going to fall off? Well, let's look back on the diagram to see where does it go from, when does it ever go from, say, 100, 104 to 75?
Joe?
Yeah.
You said as soon as you take 1 oxygen from hemoglobin, all of them easy switch off. So we basically, some of the oxygen carry all 4, and some of them just carry nothing at some point when you start to take it out?
No, it just basically you've got them carrying, say 100%. Then they're all going to lose 25%, about the same situation.
We don't sacrifice a certain.
No. But when they do lose 25%, then the next fall off pretty fast. Okay.
Changes the shape.
Elizabeth, you might tell the mom why he had this sign.
Yeah, I
Okay. All right. So here's the concentration of the tissue. So we go from 100 to 40. That's that top 25%. So where is it, when we look back at that, where is it we're seeing 140 difference? Like 100, where in the bloodstream you go from 0 or 100 to 40? So we look back, and so blood's traveling at around 100 in the main systemic arteries. So it's going to arrive here at about 100. It's going to leave, wherever it leaves, it's going to be this value over here. So it'll be leaving at about 40. So that tells you the blood's going from 100 to 40 here. And so that corresponds to going from 100 to 40. And so it's dumping here under normal circumstances, and that's O2 unloaded to tissues at rest. And so now, so that's tissues at rest. Well, once the tissues start using up and exercise and the O2 levels dropping, what it's showing is very small drops here can cause very quick unloading of the oxygen. And that's exactly what you want, because your tissues are under duress and they're needing oxygen rapidly. Whereas here, they've got all the time. It's not that big of a deal to have that much of a drop in O2 and get, you have plenty of time to get the oxygen, because the tissues themselves are at basal metabolism. They're not really have a high demand. So that's pretty cool. And it shows a little bit of that you can read a graph and interpret a graph fairly well, because you've got to think about what does this mean, this big drop, and then you have to have a little bit of understanding of why that big drop occurs. And you don't have to have a huge drop, except to understand that that cooperativity takes place. And so the first 25, the first one that comes off is fairly difficult to get it off, but once it gets off, then it makes it easier. The sites are easier to unload. They have less of affinity for oxygen, so they're going to dump it faster. Yeah.
And John, do we, for example, I work out running, whatever, and then.
You do?
I do.
Okay.
I know, I'm fat, but I do. So when we drop that 40 address, right, so we're going to the
Yeah.
capillary. So if in extensive workout, I can drop in here as well to, in the capillary to 15, if you.
Yes.
Extends, okay, good. I just want to know where it
Well,
drops.
it may never drop to 15 in the blood, because it may drop in the tissues, but I guess it will in the blood, because otherwise it wouldn't come off that fast. So yeah.
So then it reuptakes again just as quickly in that same manner.
Yeah. Yes, sir.
So you said yesterday that the limiting portion of getting O2 to your muscles and exercising was the capillaries themselves. They were
Yeah.
able to do it fast enough. So you always have excess O2.
Yeah, so that's a good question. So it might even be that the delivery is the tough part. But I've always heard that, or in various articles I've read, that one is slightly debatable where that point is, but it's almost always they end up in that final sentence saying that is the distribution, the rate that it brings it to the tissues. So here it wouldn't be a problem, because it's never limiting. So then the question is, this thing draws it down, and then, but that's a delivery that's necessary, but there still could be a problem of just the volume getting there. Even though this is dropping and getting what it can, it may not be enough.
Oh, I see.
That's my weasel way out of that. Yeah.
That may answer to sickle cell anemia.
Oh, what's your question?
So the sickle cells are shaped differently.
Yeah.
How does that change, like, the need for oxygen? Like, can they not hold as much? What
Yeah,
happens?
definitely. So they're not as efficient, because the hemoglobin itself, it becomes almost glue-like, and so they bind to themselves more than they should,
In a
which
sickle?
causes the shape to sickle.
Oh, okay.
And so, in the process of being sort of sticky, they lose their ability, well, as I understand it, they can't take up this oxygen as well, and release it as well.
Do you know about how much?
Yeah, how many can they carry?
No?
You reached the extent of my knowledge.
Thank you.
It'll be interesting to know how much actually that's shape has changed.
Yeah.
Yeah, so.
So I've never seen the articles that talk about, or the reports that talk about sickle cell anemia. They rarely talk about the two in one story. So I've never seen anybody feel the need to go to there because they're not equating the two stories. But I have an exercise physiology textbook. I'll look up sickle cell in there and see if that'd be the only place that I think they would grasp both issues. So you have to wait another 2 days. If you've extracted my working knowledge, I'll see what I can do about finding more out. That'll be a fun question to ask some of the other folks too. Okay, so we've got that, and then we're talking about, I wanted to just say a little bit about CO2. And so the CO2 is gonna, so you've got this equation, this nice little chemistry application. You've got H2O plus CO2 going to H2CO3. And then you've got this going this way here. And although this occurs fairly easily without an enzyme, it occurs much, much faster with an enzyme. But it's carbonic anhydrase. So that enzyme is in the actual red blood cells. So CO2 comes out of the tissues, comes into the red blood cells, then with the help of carbonic anhydrase, it's converted to H2CO3, which immediately goes to the bicarbonate ion and H+. H+ seems to be bound to the hemoglobin in some manner. And so it doesn't decrease the pH or decrease the pH in the tissues, apparently, or in the blood. Yeah.
The carbonic anhydrase actually dissociates H2CO3 into H+.
Goes here?
Yeah, it acts, the anhydrase means like removing a hydrogen, right?
Okay, you win. I'll look that one up too.
No, I'm just asking.
No, I don't know. Well, let's see what the book says. It might even say. Okay.
Yeah.
We're bombarding you
No,
today,
no,
John,
no.
and we're not getting
No, I think you're right. Let's see, pH water. No, it does do what you
Does it?
said.
Right.
Comes in before it forms the anhydrase. The anhydrase forms the carbonic acid.
Okay. So I'm actually right?
Yes, you're right. I was asking the question, not questioning you. Sorry.
Okay.
Because he had a sign paper.
So I've been right twice this week. That's a new record. Yeah. Okay. So back to my story here. The carbonic anhydrase causes this to happen, which then this will naturally go to equilibrium. And so these things, you can kind of think of this whole thing in relative equilibrium. And it could, as we talked about yesterday, there could be lose another hydrogen here, but that at the pHs involved is not very high concentration. So this is typically what happens. And so if you're at the tissue level, then what's going to happen is this concentration is going to increase. It's kind of neat to know that at this level, at this point in time, that all of you have had almost a full year of chemistry. So you have no oh, they haven't had it yet, is basically what I'm saying. Okay, so CO2 can increase, that's gonna cause, Le Chatelier's principle is gonna cause that movement in that direction. And so you're gonna have a net movement in that direction, and that's what's happening here. And the hydrogens are going to, by and large, attach to the hemoglobin, which, in a sense, buffers the blood against the increase in CO2, but it doesn't do it completely. Otherwise, that could not be used as a indicator by the medulla oblongata of higher oxygen demand. Okay, so then now we're ready to go. Oh, the HCO3 then diffuses out of the red blood cells and it's concentrated mostly in the blood itself, the blood plasma itself. Now we get to the other side. Here we are, the alveolar space in the lungs. And now CO2 is going to diffuse into the space because there's a higher concentration of CO2, higher partial pressure of CO2 in the blood plasma compared to the alveolar space. So CO2 is diffusing that way. So CO2 leaves, which causes everything to shift this direction. So there'll be more HCO3 coming back into the, well actually, to start from here, this leaves here, so more of the H2CO3 converts to CO2 and H2O, and that will drive more HCO3 and H plus to go that way. So the fact that more of this is going that way, in a sense, pulls hydrogen ions off the hemoglobin, which allows even more to go that way. We got that? So I want to make sure everybody gets that in here, so that if I ask it on a test, you will do well because you were here. So don't just sit and look. One more time?
One more time.
Okay. Okay, so we realize that anytime you put CO2 in water, you're going to form H2CO3, and if you've got an enzyme, harmonic anhydrase, is going to occur even faster. So you've got an almost instantaneous relationship that goes here, and think of it finally coming into equilibrium. Now, so there's a certain amount of all this, but if we're in the blood, that in the blood plasma is probably in balance, and so once we get to the tissues, there's going to be an increase here to the tissues that are exercising. So here's a cell where activity is going on and CO2 is being produced. That CO2 will drive more CO2 to react with the H2O to form this, to break down to that, which is going on here. The CO2 is coming in, it's going to react with the H2O, and now we're going to get H2CO3. That's going to break down the bicarbonate ion and H plus. H plus will attach to the hemoglobin. Apparently some CO2 does as well. And then the bicarbonate ion diffuses out of the red blood cell, and so you've got an increase in the bicarbonate ion in the plasma. And so off you go in the veins. Okay, so explain that to each other in your little groups.
Okay, so yeah, and then once you get inside the
once you get inside the blood cell.
Yeah, so once it goes to the blood, it's not balanced. And then it tries to balance itself by creating hemoglobin and having CO2 bind to that. And then it creates bicarbonate and then goes out.
It goes through the brain.
Plus,
Carbonic acid.
No, no, the CO, well, no, the CO, so you're going, you wanna go the other way?
So yeah, we breathe into the lung, and we have to transport it as HCO.
So you wanna go to the lungs? We're not talking about the lungs yet.
Okay, I'll go the other way then.
Okay, go the other way.
okay,
So we don't breathe out, carbon?
No, we don't breathe out bicarbonate.
Bicarbonate.
We breathe out,
Okay, so how about
we breathe out CO2.
It's easy out of the red blood cells.
So don't do the, if you got this, we'll go to the next one. Everybody seems to be on to the next one, so let's go there. Explain that one.
So, no, that's carbonic acid. Carbonic acid combines with H plus to form bicarbonate. And then the hemoglobin attaches to bicarbonate, which then changes it back into H2O and CO2.
Yeah, just get the blood, yes, and then we can take it away.
And then carbon dioxide leaves the blood.
so it's kind of like the opposite reaction.
Yeah, it just goes backwards.
Yeah.
So always start with CO2.
Oh, yeah.
CO2 comes in, CO2 leaves. CO2 causes the shift in the equation. And then you won't screw up.
We have a four reaction.
So CO2 is alpha and carbonic acid.
So we actually,
That was like the hardest part of the process. I was trying to comprehend that.
Okay, you do it. Okay. So this time, what's this called?
They're explaining
So
that.
there's
Hydrogen.
there's my answer right there.
It's hydrogen, carbon, no,
Trioxide.
trioxide.
So that goes in, and then you have another hydrogen.
No, wait. So CO2 is leaving.
Right, but I'm just talking about if you start with the
Has
inhalation.
water staying there, but then
Yeah.
the carbon
The other
I just want to full circle with
is
it.
released.
If you start
Okay, you start with inhalation.
If you start with the inhalation, you have CO2 diffusing across the alveolar membrane
Yes.
to the bloodstream,
Yes.
where with the aid of carbonic acid.
Wait. It's diffusing the other way. It's diffusing. We are in the lung.
Where is it?
Yes.
So if we're talking about the lungs, CO2 is going from the bloodstream to the
Right, but
alveoli.
I'm talking about the beginning of the inhalation. You have to inhale. Forget about it. I got it now. I got it.
Ruth, you always make me question myself.
No, I got it now, because I was going the wrong way. I forgot who were you.
Okay. So we got that? Everybody say yeah?
This is what I mean, coffee.
Okay, don't screw it up.
I got it now.
Okay.
Shot the H1 pulling that carbon dioxide off. It's constant.
Have you got this so that you can explain it? Okay, because when there's an enzyme here that just allows whatever's going to happen, enzymes don't do anything except allow something that happens
These are
fast,
normally
where it normally happens
40,
slowly. So, if you add, the thing about CO2 is it does react with water to form
Did you say millimeters?
carbonic acid.
It's NMHG, so
Thermodynamically,
no,
the
megahertz is H.
simplest or the
No,
uh,
it's H.
most common,
Z.
the least, most stable way of achieving, or the way of achieving stability, going with entropy. So it will just match, whereas O2 CO2 won't naturally react with water. So one of the reasons you get so much CO2 in water and you don't have to really have hemoglobin to carry it is that the CO2 will because CO2 is dissolving in here, it allows more CO2 just to be in the plasma, blood plasma. Because oxygen will just be in the blood plasma, dissolve in the blood plasma, and won't do any kind of reaction. Whereas CO2, if it gets a little bit in here, then, well, let's say it gets some in here, then some of that will go through this, and so that allows more CO2 to come in and become part of just being dissolved. So, in a weird sort of way, it increases the capacity of CO2 to end up in water. Whereas in reality, much of that is not in the form of CO2, but it's in the form of HCO3, or bicarbonate. So it's being carried, we might say that it's dissolved in water, but essentially what we mean is it's not only dissolved in water, but a lot of it's gone into carbonic acid to the bicarbonate. So it's kind of a weird conceptual thing about is CO2, did you increase the amount of CO2 and you've really increased the amount of CO2 in the air that got into the blood, not necessarily it's confounded with the idea that CO2 can dissolve in blood, but there's only a certain amount that can dissolve in blood. What makes it even more dissolved is the fact that whatever's in there, a lot of it's going to the bicarbonate ion, and so allows more to come in. Okay, so I just want to make sure, do we need any kind of, it would be best if you guys explain a few things here, or if I give you some questions that you're able to answer them. So one of the key things here is to look at this and see, oh, rest at 40. So this is the hemoglobin, this is the amount or the partial pressure of O2 in blood. And notice somehow it's we go a little bit above 100 here, and normal tissues is 40. So that's kind of key. And when we go back to this, we go, well, what are the maximum, if you looked at this drawing, I could ask, what's the maximum amount of O2 partial pressure that's ever found in blood plasma, and what's the minimum? That might be my first question under conditions shown in here at rest. So let's just, everybody tell each other so that somebody doesn't raise their hand and tell everybody and I get this false impression that everybody knows the answer. So make sure that you know the answer, quietly tell each other so that, and if you don't know, have me explain it. Because there's no point, why not do well on the test? Partial pressure.
Okay, no, I understand that. So, but at rest isn't the initial one, right?
So what's your answer?
Isn't the first one? The 60 over
And what's the lowest?
0.02.
I think 104 is,
40?
104 over 40 is
140?
the at rest.
140.
I believe so.
Okay.
And then
And if you're exercising, it's the 15 over.
So what are you guys coming up with?
45.
so at rest it's at 104, right?
Okay.
And then when you're exercising, it goes through and goes to 40.
Good.
Okay, so so at rest, so we're talking about at rest, it's 104, which, so remember that if I say it's at rest, then it's probably not, it's not going to go below 40. Here they're saying it's never going to be greater than 40, but it can be less, because at rest, it will be close to 40. But they want to hedge their bets and say, hey, look, if your exercise is going to be below 40. So this less than 40 means, okay, and if I ask, well, what happens at rest, then it's going to be close to 40. It's not going to be, you don't have to say less than 40, like they have here. If you want to say at any time, ever, then it'd be less than 40. But if I say at rest, you better come up with 40. Or give me reasons why you think it should be less. And there's possible circumstances that you might contrive that could cause you to think that would be right. Okay, so this is showing that under normal circumstances, you're going from close to 100 to close to 40 at rest. That's exciting. So here we are, close to 100 and close to 40. So given this drawing again, what's the concentration, what's the parts per million, or not parts per million, what's the partial pressure of O2, here we are in tissues, and here we are the arterial side of a capillary, and here we are at the venial side. So we pretty much haven't had any exchange, and now we've pretty much done our exchange. So what's the O2 level coming into the capillaries? What's the O2 level leaving the capillaries according to this drawing? So partial pressure, and don't say it out loud, let people think about it. Yeah, discuss it amongst yourselves, and ask me questions if you need to. And so, as you're getting that, you've got tissues, blood, and blood's flowing in and leaving. I should maybe have it in red since that's oxygen. What will be the concentration of blood according to this simple scheme in the capillaries all the way? Or will it change? So I don't have to. Yeah, partial pressure. I'm always talking about partial pressure unless I start babbling about something else.
How does it go from like 304 to 40 and back up to 120?
Okay, these are the tissues at rest. So what's it going to be in the tissues?
104.
Here and here. Okay, how are we doing? What do you think is going to be in the tissues at the beginning?
Is it gonna be, not quite sure.
Okay.
Is it gonna be 40 or is that still
Okay, so what is it when it's coming in? When it's coming in, you gotta look at the pulmonary veins and systemic arteries.
Okay.
And realize, oh yeah, it's coming in at 104. So what's it leaving as?
It would be leaving as,
In the tissue, okay.
less than 40, is that?
Well, we're talking about at rest.
At rest, oh.
And so we're pretending at rest is 40.
So it's coming in at 104, it's leaving at 40.
Okay, good. So at the beginning, it's coming in at 104 and leaving at 40. It's pretty much always 40 at rest. Because as soon as stuff comes in, it's being metabolized at a slow rate. And so it's pretty much, from the diagram anyway, we have to assume that it's going to, the tissues are big enough compared to the blood here that they keep absorbing at 40 and using it and don't really change beyond 40 all the way through. Because we have no evidence to suggest that it's going up above 40. And so there's this diffusion. It starts at 104. Now it's got to be dropping somewhere like 80, 60, and somewhere getting down to 40. Meanwhile, it's staying at 40. So there's always diffusion gradient here. It's getting less and less and less. But theoretically, by the time we're leaving, it's 40-40.
So the partial pressure of oxygen in the tissue is 40.
Yeah,
Okay.
and stays 40.
Okay.
All the way through this thing. So let's look up at, now we get into, we reverse this and think about going into the lungs. What is the blood coming into the lungs? What is the blood leaving the lungs? And we gotta go to this drawing and figure it out.
So that'd be 40 and then 120. Would be like the opposite.
I think it would be 40 to then 104.
I don't understand the top one, so that's what's throwing me off.
Yeah, the 160 and the 120 is kind of.
Yeah, that's what's throwing me off. It's like, wait, am I looking at what the exhaled air is supposed to be, or am I looking at what inhaled air
Okay,
is supposed to be?
go ahead. So what's it coming in, do you think? Coming in the,
It's coming in at 48 and then it's leaving at probably 104.
okay, so why were you doubting that?
Well, because we have two other diagrams up above for the inhaled air and exhaled air.
Okay, so that's in the alveoli. So that's in the air. So in the blood, you were exactly right. But you might have been confused by looking up at the alveoli.
Okay. I think that's what's throwing me off.
Okay, so we know that the blood's got to go from 40 to 104. Now, was in the alveolar spaces, again, a lot of this is more dynamic than we're allowing it to be. But in the alveolar spaces, that's what this is telling us. And we have to kind of assume that it's constant. And so in the alveolar space, it's 104, and meanwhile the blood's going from 60, 40, 60, 80, 104, and then out. Whereas whatever exchanges are going on around here, we're pretending it's mixing and it's fairly constant at 104. Meanwhile, the oxygen's coming in at 160 and leaving, and you're breathing it out at 120. So 160's coming in, 120's leaving, but there's always this mixing going on in the bronchioles and all the different parts of the lungs, so that on average, when it hits the small little tiny alveoli, you're getting this mixing of O2 leaving O2 coming in here, and there's mixing. So 160, and there's being drawn down to close to 104, and so now it's leaving. They're saying, well, due to all that mixing of blood, it's dropped from 160, but it hasn't gone down to 104. So it's coming in at 160, leaving at 120. Meanwhile, at the actual alveolar, it's being drawn down enough to get all the way down to 104. But according to this diagram, it's fairly constant at 104. Meanwhile, 160 is coming in, 120 is leaving. Okay. So the tissues normally are sitting at 40, but if there's exercise, then they're going to draw more oxygen. So they're going to need more oxygen. But normally they're sitting at 40, and they're not going to draw anything beyond that. So if we go to the other diagram, we've watched here at the lungs, but this is not only the lungs, this is beginning of the capillaries. The blood, the partial pressure is going in those capillaries. We just watched it go from 100 to 40. And so normally it's going to use this part of the curve. And this, because the blood's not under any kind of, because the tissues are not under any kind of stress, it's taking its time, and this, again, it's not a time diagram. This is just showing the difficulty or the ease of losing oxygen off the hemoglobin. And here it's fairly challenging because you're at that first 25%, going from 100 to 25. So that's like the tissues going from fully loaded, each hemoglobin, to having 3. All of them having 3. So they've gone from 4 to 3. 4 to 3 is 3/4, or 75%. So this is a very difficult, the oxygen is being held onto the hemoglobin fairly strongly. But because of that gradient that's always there, and you've got a fairly good distance of capillaries, it comes off. And you get it down, and there's no big deal. But now, the tissues are starting to go from 40, and they can drop like this. So instead of 40 here, we're getting draw down to maybe at least, so 20 is possible, and even less. So there's even a stronger pull here. And so theoretically then, at that point, I would expect the blood, or you could argue that the blood leaving the capillaries is at a lower level, and that's kind of what they're showing here. It's got to be. And so, but any decrease now below what's normally happening, it's very easy for the O2 to start coming off the hemoglobin. So if it didn't, then there'd be this demand for O2 and no supply. But because just even a small decrease in O2 levels makes it really easy for the O2 to come off, and that's what this curve is telling us. Okay, let's take a few minute break, and then we'll get on to go urinate, and we'll talk about it.